So welcome you to this module. Last module we started a discussion on asymptotic properties of maximum likelihood estimators. Before going to the asymptotic properties of maximum likelihood estimators, we are studying various properties of a maximum likelihood estimators. Now these properties you must have done in your earlier course, but we are just trying to refresh those properties. So what we saw is maximum likelihood estimator can be obtained by maximizing the log likelihood function. And then we said that the maximum may occur in the interior or in the boundary, and if a function is differentiable and if the maximum occurs inside theta, then it would be one of the critical points. But these critical points could also be a point of a local maxima. Then we gave our standard test from basic calculus course that how to decide about the global maximum. Now let us try to study some more properties of maximum likelihood estimators. So suppose G is a function from theta to Rp, and my estimand is G theta. Of course, one may say that if theta hat is an MLE of theta, in such situations you take G theta hat to be MLE of G theta. The way we did it for the method of moment estimators. We said that if theta hat is the method of moment estimator for theta, for any function G, you take G theta hat to be the method of moment estimator for G theta. Similar thing you can do it over here. But before that, I want to show that the estimator G theta hat also maximizes some kind of a likelihood function, which we call as an induced likelihood function. The likelihood function is induced by G theta. So let me define what is an induced likelihood function. So what I do is I consider x is fixed, that is known to us. Data is given. So Lx star eta. So let me call this as eta. Eta as G theta. So I can talk about likelihood function as a function of eta. So Lx star eta. So what is this? Now note that what may be happening is for a given eta, more than one point may be going. So this is the image of the set theta. So each theta naught, theta 1, or theta 1, theta 2, theta 3, more than one points may be going to the same eta. So what I try to look at it is which population has a maximum likelihood of giving this eta. So that means I try to look at what is the supremum over all those theta belonging to theta, such that G theta is eta. So among all these theta i's, which one has a maximum chance of giving this eta? And then I look at Lx theta. Now this is called, so this is a function of a estimand, eta. So this is called likelihood function induced by eta is equal to G theta. So considering my induced likelihood function makes sense because of the reasoning I gave. This eta is represented by more than one populations. So I look at among all those populations which has the maximum chance of giving this eta. That is what Lx star eta is for a given data point. Now one may think of maximizing this and then taking that estimate as the maximum likelihood estimate of eta. So we call it the MLE of eta hat of eta is defined by. So what I do it, I try to look at the one which maximizes this. So that means Lx star eta hat should be same as supremum over eta belonging to lambda of Eta hat, of course, would be a function of observations. Lx of eta, where lambda is basically the image of the set theta, which is basically correction of all those g theta such that theta belongs to capital theta. Because these are the set of possible values which the estimate can take. So the MLE of any function of theta can be defined in this way. So certainly, if I take my G to be identity map, I should get the same estimate. So that means in the situation where G is same as identity map, this function should be maximized by theta itself. In fact, I'll prove in general that if theta hat is an MLE of theta, then G theta hat is an MLE of G theta. So that is what the next result is. So theorem, if for given observation theta hat x is the MLE, even if it is an MLE, is an MLE of theta, then G theta hat x is the MLE of eta, which is G theta. Let me not give a proof of it. I'll leave this as an exercise. But let us try to see if you have to show that this is an MLE of this. So what you have to show? You have to show that G theta hat x maximizes this quantity. So that means what you have to show is Lx star eta hat x, which is G of theta hat x, maximizes that. So that means this is same as supremum of eta belonging to lambda of Lx eta and Lx, sorry, this would be Lx star eta. Of Lx star eta, and Lx star eta is given by this supremum over. So let me write down for the time being Lx star eta. That is, now I write down the value of Lx star eta, so that means supremum over all those theta belonging to theta, such that G theta is equal to G theta hat x of Lx theta is same as supremum over, so this supremum I can write down over here, supremum of all those theta belonging to theta, such that G theta is equal to eta, and then supremum over eta belonging to lambda of sorry, supremum over, first would be eta, supremum over all those eta, such that, yeah, supremum over all those eta belonging to lambda, and then supremum over of Lx star eta, which is same as supremum over all those theta belonging to theta, such that G theta is equal to eta of Lx theta. Now note that Lx theta hat maximizes Lx theta. So using that property, you can prove this. I leave this as an exercise. Let me not spend, the proof is not difficult. Now, what I'm going to do is I'm going to do a result which tells you that maximizing likelihood function is very intuitive appealing. To do that, first let's add some assumptions. The first assumption is my model is identifiable. Identifiable means, that means if for two different theta i's my probability distributions are same, then theta 1 has to be same as theta 2. So that means two different points in parametric space cannot give me the same probability distribution. So my parameters are identifiable for theta 1, theta 2 belonging to theta. If my f theta 1 is same as f theta 2, so that means distribution function at theta 1 is identically same as distribution function at theta 2, this happens if and only if theta 1 is same as theta 2. So that means my family is identifiable. That is P, which is f theta, theta belonging to theta, is identifiable. Or in other words, my parameter theta is identifiable. The second assumption is each of these f theta have the same support. So that means if I change theta, the support should not be different. Or in other words, my support should not depend on theta. So the support of, so the distribution functions f theta, theta belonging to theta, have the same support. That means it does not depend on theta. That is basically what means is support of f theta does not depend on theta. Then the third property is my theta is an open set. So that means considering the point on the boundaries is ruled out. Now following theorem which I am doing give you a theoretical justification why one should try to maximize the likelihood function. So I am trying to develop a theoretical justification for maximizing the likelihood function, or equivalently a log likelihood function. So let us try to do that result. So suppose, so first say suppose assumptions A1 and A2 hold. And let then what should happen? That means I am saying that Lx theta, maximizing Lx theta makes sense. Or in other words, I should try to find out what is the expected value of Lx theta under the true parametric value theta naught. And that should be maximum at the true parametric point only. Or in other words, what should happen is if true parametric point is theta naught, then Lx theta naught should be the maximum. So that means expected value of Lx theta naught should be greater than when theta naught is the true value and Lx theta for every theta naught equal to theta naught. So what it says is when theta naught is the true parametric value, expected value of Lx theta is maximized when theta is same as theta naught. So that means maximizing Lx theta that way makes sense. Because E theta naught means theta naught is a true value. So E theta naught is the same on both the sides. This represents the fact that theta naught is the true value. Theta naught is the correct value of the parameter. If theta naught is the correct value of the parameter, then expected value of likelihood function is maximum when theta is same as theta naught. So that means I should try to maximize Lx theta. Similar thing holds for in terms of probability. So for any theta naught equal to theta naught, probability when theta naught is the true value, Lx theta naught is greater than Lx theta. So that means when theta naught is the true value, the probability that likelihood function at theta naught is bigger than the likelihood function at any other point theta, that should be 1. So these are strong justifications for maximizing the likelihood function. So the proofs are not difficult. Let me just give a proof. So let us consider theta naught equal to theta naught. Then Lx theta minus Lx theta naught this is a log of Lx theta minus log of Lx theta naught, which is nothing but log of Lx theta by Lx theta naught. So expected value under theta naught of Lx theta minus Lx theta naught would be expected value of log of Lx theta naught. Now log is coming. I can think of using some standard inequality. And you know, log is a concave function, or minus log is a convex function, because if you take the second derivative of log of x for x positive, it turns out to be minus 1 upon x square, which is negative. And if second derivative is negative, then you know that function is concave. Now if function is concave, then you know that expected value of h would be less than or equal to h of expected value of x. So this would always be less than or equal to L of E theta naught of Lx theta naught. But what is this quantity? This is nothing but log of expected value means I can talk about integral or summation depending on Lx theta divided by Lx theta naught and expectation is under theta naught, so that is g theta naught x d mu. D mu could be a sign measure or Lebesgue measure depending on whether you have a discrete case or continuous case. But likelihood function is nothing but the density, right? That is way of defining. So gx theta is nothing but g theta, sorry, I can now here put small x, right? Because x was a random variable. So this would be g theta x by g theta naught x, g theta naught x d mu, g theta naught cancels, and it is integral of the whole density g theta x, which is 1, and log of 1 is 0. So what do you get? Ex of log Lx theta minus Ex of Lx theta naught, its expected value is less than or equal to 0, or E theta naught of Lx theta would be less than or equal to E theta naught of Lx theta naught. So that proves the first part. How do you prove the second part? For theta naught equal to theta naught, actually this would be limit n going to infinity as sample size goes to infinity. So for theta naught equal to theta naught, let us consider Tx, which is log Lx theta minus log of Lx theta naught. This was product I is equal to 1 to n, joint was, so this is log of, so this whole can be written as 1 upon n, summation I is equal to 1 to n, log of f theta xi by f theta naught xi. Right? Because Lx theta was product I is equal to 1 to n, f theta xi. So log with the product would give you sum. This also would give you a sum. So sum you can take common, and then this becomes this. F theta x upon f theta naught xi, they are IID, because xi's are IID. So this is, so log of this would also be IID. It's the same law. So what you have? It is a mean of IID observations. And by strong law of large numbers, you know that this goes almost surely to expected value of this quantity. So expected value of, when theta naught is a true value, log of f theta x1 by f theta naught x1. Again, you use Jensen's inequality. This will always be less than or equal to log of E theta naught of f theta x1 by f theta naught x1. Now, the way you did it over here, this would also be 1, and so this would turn out to be 0. So log of 1, which is 0. So what do you get? So probability that theta is less than, sorry, this would be Lx, log is already there in Lx, right? So probability that Lx theta is less than Lx theta naught is same as probability that Tx is less than 0. And you have seen that as n goes to infinity, Tx goes to some quantity less than 0. So this is goes almost surely. So this one. So that proves that your likelihood function, probability that likelihood function at point theta is less than likelihood function point at theta naught, that probability goes to 1 as n goes to infinity. So these two properties, in fact, justify maximizing the likelihood function. So it, in certain sense, justifies the optimal property of maximum likelihood estimator. So maximum likelihood estimator that way has a lot of intuitive appeal in terms of these results. So what I can do now is I can come to now asymptotic properties of maximum likelihood estimators. So the first thing which we need to see is, because the easiest way which you have been doing so far to find the maximum likelihood estimator is just concentrate on the critical point. So the first result which I am going to do about maximum likelihood estimator is about the nature of critical points, more than one critical points. How to go about it? Can I say that one set of critical points would have some asymptotic properties? Or can I say that there would always exist a sequence of estimators theta n hat, sequence in the sense that they depend on the sample size. Theta n hat says that theta n hat would be a critical point. Theta n hat will converge in probability to the true parametric value theta naught. Now, if That happens if I can prove that result. That means there will always exist a sequence of estimators theta n hat such that probability that theta n hat x is a root of those likelihood equation, that probability goes to 1 as n goes to infinity, and probability that theta n hat x is a local maxima, that probability goes to 1 as n goes to infinity, and theta n hat x converges in probability to theta naught. If I can prove that result, we'll see that we'll be in a position to identify maximum likelihood estimators in a straightforward manner in certain situations. So let me stop over here. So next time, in the next module, I'll study some of the optimal properties of, some of the optimal asymptotic properties of the maximum likelihood estimator. So thanks. See you in the next module.